According to Section 702.5 of the National Electrical Code, it is not a requirement to change out an existing main breaker to match the smaller fuse size of a fusible transfer switch. Section 702.5 addresses the requirements for the connection of optional standby systems. The relevant portion for this scenario focuses on the overcurrent protection requirements when connecting a generator or other optional standby power source through a transfer switch. Specifically, the code stipulates that the transfer equipment, including the fusible transfer switch, must be suitable for the intended use and be so installed and connected as to facilitate testing and maintenance. This implies that the transfer switch needs to be appropriately sized for the load it will carry and the available fault current. The part of the code that is relevant is overcurrent protection. The overcurrent protection, typically fuses or circuit breakers, must be selected and coordinated to protect the transfer equipment and the connected load. Section 702.5 states that the overcurrent protective devices for the optional standby system shall be selected to provide protection for the connected equipment and circuits. This means that the fuse size in the fusible transfer switch needs to be adequate for the load it is intended to serve and should not be less than the ampacity of the conductors connected to it. However, the code does not explicitly mandate that the existing main breaker be replaced simply because it is larger than the maximum fuse size of the fusible transfer switch. The key is to ensure that the fuse size in the transfer switch is appropriately sized for the load and the conductors it protects. Here's a more detailed breakdown. Firstly, the main breaker's purpose is to protect the entire electrical system of the building from overcurrents and short circuits. It is sized based on the total calculated load of the building, considering various factors such as lighting, appliances, and equipment. Secondly, the fusible transfer switch is designed to safely switch between the normal power source and the optional standby power source, typically a generator. The fuses in the transfer switch protect the generator and the load connected to it during generator operation. They also provide a level of isolation between the two power sources. Thirdly, the NEC requires that the transfer switch and its overcurrent protection be suitable for the intended use. This means that the fuse size should be adequate to handle the load transferred to the generator without nuisance tripping, but it should also provide sufficient protection against overcurrents. Fourthly, if the existing main breaker is larger than the maximum fuse size of the transfer switch, it does not automatically violate the NEC. The main breaker's primary function is to protect the entire building's electrical system, while the transfer switch's fuses protect the generator and the load it serves during generator operation. Fifthly, the NEC does not explicitly require replacing the main breaker in this scenario because the two overcurrent protective devices serve different purposes and protect different parts of the electrical system. The main breaker protects the entire building, while the transfer switch fuses protect the generator and the load connected to it during generator operation. Sixthly, it is essential to ensure that the fuse size in the transfer switch is properly coordinated with the generator's output and the connected load. This coordination ensures that the fuses will trip before the generator is overloaded or damaged. Seventhly, if the engineer on the job is requiring the main breaker to be changed out, it may be based on specific design considerations or local codes that go beyond the basic NEC requirement. It is crucial to understand the reasoning behind this requirement and to ensure that it is justified by the specific circumstances of the installation. Eighthly, it is always a good practice to consult with a qualified electrical engineer or inspector to ensure that the electrical installation complies with all applicable codes and standards. They can provide valuable insights and guidance based on their expertise and knowledge of local requirements. Ninthly, in summary, the NEC does not mandate replacing the existing main breaker simply because it is larger than the maximum fuse size of the fusible transfer switch. The focus should be on ensuring that the fuse size in the transfer switch is appropriately sized for the load and the conductors it protects, and that it is properly coordinated with the generator's output. Tenthly, it's crucial to understand the coordination between different overcurrent protection devices within an electrical system. Overcurrent protection devices, like circuit breakers and fuses, are designed to protect electrical circuits and equipment from damage caused by excessive current flow. This excessive current can result from overloads, short circuits, or ground faults. The goal of overcurrent protection is to quickly interrupt the flow of electricity when a fault occurs, preventing damage to equipment, reducing the risk of fire, and ensuring the safety of personnel. Coordination of overcurrent protection devices refers to the selective tripping or clearing of only the affected portion of an electrical system during an overcurrent event. This means that the overcurrent device closest to the fault should trip first, isolating the fault while allowing the rest of the system to continue operating. Effective coordination minimizes downtime and prevents unnecessary interruption of power to critical loads. Several factors influence the coordination of overcurrent protection devices. Firstly, time current curves are graphical representations that show the operating characteristics of overcurrent devices. These curves plot the time it takes for a device to trip at various levels of overcurrent. Coordination studies involve comparing the time current curves of different devices in the system to ensure that the downstream devices trip before the upstream devices during an overcurrent event. Secondly, the ampacity of conductors is the maximum current a conductor can carry continuously without exceeding its temperature rating. Overcurrent protection devices must be sized to protect conductors from overloads and short circuits. The size of the overcurrent device should not exceed the conductor's ampacity. Thirdly, the interrupting rating of an overcurrent device is the maximum fault current that the device can safely interrupt without being damaged. The interrupting rating must be sufficient to handle the available fault current at the device's location in the electrical system. Fourthly, different types of overcurrent devices have different operating characteristics. For example, fuses typically have faster tripping times than circuit breakers, especially at high fault currents. The selection of the appropriate type of overcurrent device depends on the specific application and the desired coordination characteristics. Fifthly, coordination studies are essential for ensuring proper coordination of overcurrent protection devices. These studies involve analyzing the electrical system to determine the available fault currents at various points and then selecting and coordinating the overcurrent devices to achieve selective tripping. These studies are typically performed by qualified electrical engineers using specialized software. In a specific scenario of a Fusible service entrance rated manual transfer switch, coordination with the main breaker is important. The main breaker protects the entire building's electrical system, while the fuses in the transfer switch protect the generator and the load connected to it during generator operation. The fuses in the transfer switch should be sized and coordinated to protect the generator from overloads and short circuits. They should also be coordinated with the main breaker to ensure that the fuses trip before the main breaker during a fault on the generator side of the transfer switch. If the existing main breaker is larger than the maximum fuse size of the transfer switch, it does not necessarily mean that the main breaker needs to be replaced. The focus should be on ensuring that the fuses in the transfer switch are properly sized and coordinated to protect the generator and the load connected to it. The engineer's requirement to change out the existing main breaker may be based on specific design considerations or local codes that go beyond the basic NEC requirements. It's crucial to understand the reasoning behind this requirement and to ensure that it is justified by the specific circumstances of the installation. Always consult with a qualified electrical engineer or inspector to ensure that the electrical installation complies with all applicable codes and standards and that the overcurrent protection devices are properly sized and coordinated to provide adequate protection and minimize downtime. The goal is to achieve a balance between protecting the electrical system and ensuring that critical loads remain operational during an overcurrent event.